Have you ever wondered how information travels on the internet? Have you thought about how passwords and credit card numbers are stored on websites? What makes you feel safe while communicating and making transactions on the web? How are emails hacked? How are you even watching this video right now? No need to fear, for RSA cryptography is here. Well, it actually has existed for almost 40 years now. What is this magnificent algorithm that holds the key to secrecy? Simply put, RSA is a public key crypto system. Crypto systems encode and decode information, and cryptography is the mathematical study of solving these codes. Public key cryptography is used to send encrypted or encoded information from one person, Alice, to another, Bob, using public and private keys. For Alice to send Bob a message, Bob must initially release his public key. This public key will be used by Alice to encrypt messages she sends him. At the same time, Bob must keep secret a corresponding private key he will use to decrypt messages. The system is almost like that of a lock and key. Alice secures her message with Bob's lock, and only Bob can open it, as he holds the sole key. Each of these keys consists of a pair of numbers, and pretty large ones at that. In fact, the strength of RSA lies in their enormous size. Let's see how these numbers are generated. First, Bob selects a random large number. How large? Nowadays, 1024-bit keys are the general standard for security, though this will change as time goes on. A number has 1024 bits if it has 1024 digits in binary. This would correspond to about 309 decimal digits. Next, Bob will check if the number is a prime. Need a refresher on what the primes are? A number is prime if it has two positive divisors, 1 and itself. Using fancy primality tests, Bob should be able to find a number that is almost guaranteed to be a prime pretty quickly. By almost guaranteed, I mean the probability of a composite being falsely labeled as a prime is on the order of 10 to the power of negative 29. Bob will need two different primes for the algorithm. The next thing Bob has to do is multiply the two primes, say p and q, that he has found. Bob will denote the product p times q as n, the modulus. Finally, Bob just needs to select integers e and d, such that the product e times d leaves a remainder of 1 when divided by the product p minus 1 times q minus 1. This number e will be the public key exponent, and d will be Bob's private key exponent. The public key will be released as the pair n, e, and Bob will keep the private key n, d secret along with the primes p and q. How do these bizarre numbers allow us to use the algorithm? Let's walk through an example. It's Bob's birthday, and Alice would like to send him a message on this notable occasion. She wisely decides to employ the RSA algorithm. She translates her message into a numerical value m, and encodes it using Bob's public key e. To do this, she computes the remainder x that m to the power of e leaves when divided by n. She sends Bob the value x. Once Bob receives x, all he must do is compute the remainder x to the power of d leaves when divided by n. Bob can finally read Alice's happy birthday message thanks to RSA. What makes RSA so strong? Currently, the only known way to break RSA encryptions is to factor n, the modulus. However, factoring n in the public key is very difficult, as its prime factors are insanely large. The fastest factoring algorithm developed for classical computers is the number field sieve, which broke a 768-bit RSA modulus in 2009. This still stands as the current record for factoring. However, we are a long way from factoring commonly used modulus sizes. How long would it take to break a 2048-bit modulus? The company Digicert estimates that it would take over 6 quadrillion years for a standard desktop computer to break one of these encryptions. The RSA algorithm, a breakthrough, get it, in the field of cryptography, was invented by Ron Rivest, Adi Shamir, and Leonard Edelman at MIT in 1977. It's natural to ask what lies ahead for RSA and public key cryptography as a whole. Quantum computers threaten the safety of public key crypto systems. In 1994, Peter Shor solved the problem of factorization using quantum computing. Shor's algorithm is understandably much faster than the number field sieve. However, the field of quantum computing is young, and they are far from factoring even small numbers. In fact, the largest number that has been factored using Shor's algorithm is 21 equals 3 times 7. Achieved in 2012. Overall, the invention of RSA has revolutionized cryptography and cybersecurity. Not only has it allowed us to use the web, it has spurred research in math, physics, and computer science. Yet, post-quantum crypto systems are being studied as RSA will be deemed insecure in the future. In the words of Alan Turing, "We can only see a short distance ahead, but we can see plenty there that needs to be done.